Let me summarize this presentation as follows. First, the Karl-Fischer titration is an oxidation-reduction titration in non-aqueous solvents. Iodine and water react quantitatively, 1 mole to 1 mole, in this reaction. The change of the polarizing potential can be detected due to the reaction between iodine and iodide anions. Substances exist for which the water cannot be measured. Some types of substances can be measured by selecting suitable reagents, for ketones, for example, or by adding salicylic acid. Some thermally unstable substances can be measured with the optional water vaporizer. Second, the Karl-Fischer titration is applicable for various kinds of samples with a wide range of water concentrations. Colorimetric titration is suitable for low moisture samples, and volumetric titration is suitable for high moisture samples. It is applicable for liquids, gases, and solids by selecting suitable reagents. Third, the Karl-Fischer water measurement method is highly reliable and can be the standard water measurement. There are other methods to measure the water or moisture content, such as measuring loss on drying, using near-infrared absorption spectroscopy, employing gas chromatography, and so on. Let me suggest that the Karl-Fischer titration is the most useful method due to its wide-ranging applicability and that it has become a standard for water measurement due to its accuracy and reliability. Thank you kindly for your attention. I will now explain, in the following 8 slides, the details of our AQUAMICRON Karl-Fischer reagent products and some supplementary information, some notes about their practical use, for example. We provide 32 grades of AQUAMICRON Karl-Fischer reagents, which are classified into 4 categories and tabulated in this slide. Regarding volumetric titration, there are 2 grades of titrants, SS and SSZ, and more than 10 grades of dehydrating solvents that correspond to them. The SS series titrants are made mainly of chloroform and pyridine, conforming to the original compositions that Dr. Karl-Fischer described. They were developed in 1950 by Mitsubishi Kase, the former incarnation of Mitsubishi Chemical, and have been in distribution for more than 60 years. The SSZ series titrants are made of imidazole instead of pyridine in the SS series, and they contain less chloroform than the SS series. All the dehydrating solvents, except those for ketones, can be used generally with both titrants, SS and SSZ, though they are categorized into these 2 series. When you measure ketone samples, you have to use the titrant and the dehydrating solvent in the same series, SS or SSZ, and you do not need either to prepare another specified titrant or to exchange glass burettes. This is one of the features of AQUAMICRON. In colorimetric titration, the cathode solutions, or CXU series, are commonly used for all purposes except single-solution titration. This is another feature of AQUAMICRON. Now, I would like to describe the main constituents, or chemical compounds, of AQUAMICRON and the corresponding regulations due to their physicochemical properties. This table shows almost all the organic solvents such as methanol, propylene carbonate, diethylene glycol monoethyl ether, chloroform, pyridine, and others. You can use this table to select the proper grade by considering the sample solubility in such solvents. Most of the Karl-Fischer reagents are regulated in Japan by the following 3 laws: the Fire Defense Law, the Poisons and Deleterious Substances Control Law, and the Chemical Substances Control Law, or Pollutant Release and Transfer Register Law. Firstly, with regard to the Fire Defense Law, all the solvents are flammable liquids categorized in Class 4 of hazardous materials, except the titrants SS series and the dehydrating solvents CM and CP series, which are non-hazardous materials since they have no flash points due to their high concentrations of non-flammable chloroform. Secondly, regarding the Poisons and Deleterious Substances Control Law, there are no poisons in AQUAMICRON products under this law. We are frequently asked by our customers about why AQUAMICRON products are not considered poisons, since iodine, methanol, and chloroform are all poisons. This is because, although the pure forms of these substances are surely designated as poisons, the mixtures or the formulations of iodine, methanol, and chloroform are not designated as such. Thirdly, chloroform and pyridine are regulated by the Chemical Substances Control Law. Thus, their concentrations in the products are indicated in two significant numbers, both on the labels and in the MSDS, for customers to calculate the quantity consumed in accordance with the Pollutant Release and Transfer Register Law. Here is a flowchart that will help you select the most suitable AQUAMICRON grades depending on the water content, the nature, and the physicochemical properties of your samples. I would like you to refer to the same flowchart illustrated on page 199 of the technical manual when you measure new kinds of samples. Now I will describe some points that I would like you to keep in mind for the practical use of Karl-Fischer titration. The first point, in the case of volumetric titration, is that you will have to use the titrant of the same series as of the dehydrating solvent when you use, for ketones, dehydrating solvents. More specifically, if the dehydrating solvent is KTX, the titrant should be SSZ, whereas the titrant should be SS if the dehydrating solvent is CP or PE. The second point also concerns, for ketones, dehydrating solvents. When you use the dehydrating solvent KTX, if you seldom use it, you sometimes cannot reach the endpoint smoothly. In these cases, I recommend that you amend the setting of the endpoint potential a little higher, lest you waste your time and titrant on over-titration. The endpoint potential can be changed manually in most analyzers, but if you cannot determine how to handle it, please contact us. Third, when you use, for sugars, dehydrating solvents, SU or FM, and the dehydration is not completed, please add some salicylic acid to the solution. These dehydrating solvents, SU and FM, are both mixed solvents of methanol and formaldehyde. The latter, formaldehyde, is in storage apt to decompose to form alkaline ammonia that hinders the Karl-Fischer reaction, the preferable pH of which is 4 through 7. Salicylic acid works as a neutralizer against ammonia. You might think that salicylic acid could be added beforehand, but this does not work since it reacts with methanol and forms esters and water. Thus, you can add salicylic acid only when the dehydration does not seem complete. Fourth and last, when it is difficult for the sample to dissolve in the dehydrating solvent, you may add another proper solvent that never interferes with the Karl-Fischer reaction, the volume of which is some 30 or 50% of the dehydrating solvent. Such proper solvents are listed under the heading Organic Compounds on page 37 of the technical manual. Some examples are toluene, gamma-butyrolactone, GBL, and isopropanol. Next, in colorimetric titration, while you use the water vaporizer, you may sometimes be tempted to add AQUAMICRON AX to the sample solution because its volume is decreasing gradually. I would like to remind you that you should add methanol for this purpose instead of AQUAMICRON AX. The second point concerning colorimetric titration is that the anode solution for ketones, AKX, should not be used for ordinary samples. It should be used only for samples that interfere with the Karl-Fischer reaction, since it has two disadvantages vis-à-vis the other anode solutions. One of these disadvantages is that the total amount of water content that can be measured with it is much less than the other solutions. The other disadvantage is that the measured values are inclined to be lower than the actual values due to side reactions. In this slide, I will let you know when or how you should decide to exchange the reagents with new ones. To put it simply, you should exchange them when the polarizing potential becomes unstable and the endpoint is difficult to determine, or when the accumulated water amount that has been measured with the reagents reaches the upper limit level, the typical values of which are listed in the table in this slide. There is also another, more practical way. As I already explained in slides 9 and 10 about general analytic procedures and maintenance, when you encounter some abnormal phenomenon, you should consider exchanging reagents. The quality assurance term is determined based on the manufacturing date, not on the purchase date. You can find the month and year of manufacture by the lot number on the label. The second and the third numbers indicate the year, and the first number indicates the month. The label also shows the expiration date of the quality assurance term. Almost all AQUAMICRON products have 5-year quality assurance terms. The exceptions are 3 years for standard samples and 1.5 or 2 years for titrants. Since the potency of the titrant may change gradually in storage, its term is the shortest.